Hello everyone, welcome to another section of the lecture series on measure theoretic probability. So today on lecture 5, we will be talking about the Dynkin's pi lambda theorem. We will talk about the uniqueness in our lecture 6. But before this, just a quick reminder that we talk about general measures. So we said that a measure is sigma finite if there is a finite or countable sequence a1, a2 through to infinity that belongs to what f, such that when you pick the whole space, it could be expressed as a countable union of these AKs. And when you pick each AK, the measure should be what? Should be finite. Then the measure is called what? A sigma finite measure. The question is the counting measure? Is the counting measure on R or on the unit interval a sigma finite measure? The answer is what? No. Since when you pick the unit interval and R, they are what? Uncountable. Because the counting measure has to count the number of elements, and this interval it can't count because there are many AKs in it. You can't actually count it. Like there are many elements within this interval, you can't actually count it. So let's talk about an interesting theorem. So theorem: a measure on a field has an extension to the generated sigma field. Moreover, if mu is a sigma finite, then this extension is what? Is unique. We return back to one of our previous lecture. So here, remember we talk about existence and extension theorem. So we are going to return back to that lecture and we prove the uniqueness aspect of it in our lecture 6. But before we do that, we need to develop some kind of machinery that will help us prove that. So here we develop some machinery. To prove the uniqueness in the existence and extension theorem. The case of probability measure. So here the mu that we're going to take should be a probability measure, and that measure to be a sigma finite measure. All right. Okay. So this machinery that we want to develop is called the Dynkin pi lambda theorem. What is the motivation behind this? It is often difficult to work with sigma fields. Often it is easier to show a result on a simpler class of sets. So here we introduce two different class of sets, and that class is called the pi system, and that of the lambda system. And here comes the name, the Dynkin pi lambda theorem. So what do we mean by a pi system? So definition: a class P of subset of omega is called what? It's called a pi system if this condition holds. If you have A1, if you have A and B belonging to that class, then their finite intersection should also belong to that class. So here P is also it's a field. You just need to include a condition that the whole space also belong to it. And since you have some finite elements and their finite intersection also belongs to it, then that class is it's a field. We are going to actually talk about that in our next lecture. So this class is called a pi system. Next, definition: a class L of subset of omega is called a lambda system if, first of all, condition 1, lambda 1, that is the whole space belongs to that class. You're going to see that this class is more like it's more like the sigma field, but it's not a sigma field. So there is a certain thing you need to note. By condition 2, if you have A belonging to the class, then it implies that its complements must also belong to that class. By condition 3, if you have A1 through to infinity that belongs to that class, then we need the A1, we need AN intersection AM to be to be disjoint. This implies that if we have AN intersection AM, it should be equal to the null set or the empty set for M not equal to N. And therefore, if you take the countable union should also belong to that class. So here we stress much on the disjointness of these sets when M is not equal to N. So we ask ourselves a question: is it true that any sigma field is a lambda system, but a lambda system is not a sigma field? So the answer is is yes. All right. So we are going to show the results on this. Okay. So lemma, a class that is both a pi system and a lambda system is what? It's a sigma field. So here we are going to talk about a class, and we need to include the conditions for what? For that class to be what? A pi system, and out of what? A lambda system. And in addition, if you add them together, they produce what? A sigma field, which is also what? Another what? Class. So here we wouldn't denote the class by any kind of Greek letter. We are going to talk about the class. Know that it's a subset of what? The omega. And this class has both the conditions for what? A pi system and that of what? A lambda what? System. So the proof. This class contains what? The whole space because of what? Lambda 1. And this class is also closed under what? Complements by what? Lambda 2. And it is also closed under finite what? Intersections by what? The pi condition, the pi system condition. Here we conclude that this class is what? Is a field. So now we want to include the countable aspect of what? Of the elements in it. So we are saying that let A1 true to infinity be elements of what? Of this class. We need to show that the countable union also what? Belongs to what? To that class. Are you okay? Then, but before then, we need to satisfy the condition for lambda 3. Because we talk about lambda 2, lambda 1, lambda 2, and a pi. So we need lambda 3 in addition. But lambda 3 needs disjointness in this class. But this condition that we just introduced doesn't include disjointness. So we introduce another what? Elements. So let's say B1 equal to what? A1. B2 is equal to A2 remove our what? A1. So you are creating disjointness within what? This class. Here you realize that B1 intersection B2 is what? Is the empty set. And we keep on creating what? Such what? Disjointness within this class. So this sequence is disjoint. And hence by lambda 3, the countable union of this Bi is an element in what? In this class. But note, the countable union of this Bi is equal to what? The countable union of this of these AIs, and hence the AIs are also what? Disjoint, and AIs, the countable union of these AIs, needs to also belong to what? To this class. So we satisfy the conditions needed for this class to be what? To be a sigma field. Thus, this class is what? Is a sigma field. So now we introduce our theorem. We say that the Dynkin pi lambda theorem states that if P is a pi system, now we know what a pi system is, and L is a lambda system, then the pi system is a subset of what? The lambda system. It implies that the sigma field generated by that pi system is a subset of what? Of the lambda system. So I repeat, the Dynkin pi lambda theorem. If P is a pi system and L is a lambda system, then P is a subset of L, then it implies the sigma field generated by P is a subset of L. So we are going to use this machinery to actually prove the extension of a measure on a field being extended to what? To a sigma field. Thank you, and see you in my next lecture.